Okay, good morning, everyone. Happy Halloween. I'm a little disappointed to see no costumes this morning. In case you can't tell, I'm dressed up as a professor who's very excited for reading week coming up in a couple of weeks. I hope that things weren't too difficult on Wednesday with the video replacement lecture. Last day by video, you were introduced to the different modes of elastic buckling. I hope everyone watched it and was introduced to the different modes of elastic buckling. The first day we talked about this equation for calculating compressive resistance. This is really the only ultimate limit state, so to speak, that we're going to be formally calculating and checking. We haven't quite yet talked about where this subscript E may come into play, but that's what we're going to talk about today. Last day, you also saw, in addition to the elastic buckling from Euler's elastic buckling load for weak or potentially strong axis, there is also potentially the ability for certain sections to buckle torsionally. And basically what you have to do is calculate the FE values for the weak axis, the strong axis, and the Z axis, which is twisting. And depending on which value of FE is the smallest, you use this FE value to calculate lambda and use that value of lambda to calculate CR. So we still haven't really talked much about the K or L values. When I introduced the expression for calculating CR the previous day, Monday, we basically said, well, it's based on lambda, and we're going to calculate lambda based on FE. And in the example, we just did K is 1 and L was L. And we'll talk next day about situations when that might not be the case. Today, we're going to focus on this little expression that's shown here. Basically, we're going to see a certain plate width divided by the certain plate thickness. Has to be less than or equal to a certain number divided by the square root of Fy. And that looks weird. You probably haven't seen anything like that before. We're going to talk about what the ratio on the left means, what the ratio on the right means, and what it is we're doing when we're actually checking this expression. And what that means is today we're going to be talking about something called local buckling. So far, everybody should have a relatively solid understanding of what global buckling means. Something's buckling by bowing outwards along the full member length or twisting along the full member length. Today we're going to talk about situations where components of the elements actually buckle locally, and so most of our sections in structural steel are sort of built up out of kind of different plate sections. So we're going to see sometimes the flange or the web can actually have a little bubble pop out, and that phenomenon when we have those little local pops of flange or web buckling out under compression is called local buckling. Right, so we do have these primarily uncoupled modes of global buckling for wide flange sections. If we're buckling about the weak axis, the whole thing bows out to the left in this case. If we're talking about global strong axis buckling, it's buckling more into the page, or we could have this potential for twisting. And what we're going to see is that this expression that we have for calculating the global buckling strength, if local buckling becomes a problem, we're going to simply modify the equation here to include an A subscript E. And we're going to talk about when we need to calculate that value of AE and how we calculate that value of AE when required. So what does this look like? Well, these sections can basically, once they experience some kind of axial compression, the flange or the web can start to buckle in this sort of strange looking waveform, right? So the flange can kind of buckle something like that. And what that's basically going to mean is we're not going to be able to apply as much stress to the cross section, because usually when this happens, it means that we're going to buckle the flange or the web before we start to get yielding of the cross section. And so this is technically an ultimate limit state. If we get local buckling, that's something that's going to govern the strength of our members. And so we need to know how to quantify the effects of local buckling on strength. It's not just the fancy numerical analysis that I can show you on the previous slide, but this has been observed in experimental tests as well. And so we can see similar phenomenon here. Basically in these tests, there were some stubs of wide flange section, just support on the bottom and push down on the top with a hydraulic actuator. So that actuator is pushing down on the section, and before they got yielding of the cross section, basically before they reached the load AFY, we got buckling of the flange, and that reduced the load that could be applied to the cross section. Okay, so basically after this, you should be able to describe that local buckling effect in members under axial compression, check whether a section is likely to experience local buckling before cross-section yielding, and ultimately calculate the effective area of sections that might be susceptible to local buckling for global buckling resistance calculations. Does anyone have any questions about those three things or why they're important before we continue with the technical material? Okay, so let's cross my fingers and hope that this works. Oh, I just had it there. I think I can unlock it. Should be active. The 42 seconds might not quite be enough, but go into pull everywhere. I've got an answer, or 5 answers to a question I don't think you should know the answer to, but I'm just curious if you read this. Local buckling is most likely to affect. There are a bunch of different kinds of answers. Maybe it's more likely to affect short columns. Maybe it's more likely to affect long columns. Maybe you've got intermediate columns that we talked about on Monday. All lengths of columns, or maybe you're not really sure what kind of column local buckling is most likely to affect. I really shouldn't have the time limit on there. I'm not sure why it is there. If you didn't get the opportunity to participate and you wanted to, that's quite okay. And this is interesting. I always find that most people will lean towards short columns, and that's the right answer. But usually when I ask people, they're not really sure why, and maybe I'll ask a few folks later on. I have all these different answers because when we talk about global buckling, longer columns are more likely to buckle, right? And so the longer L gets, the lower the elastic buckling L gets, and the smaller the compressive resistance is. However, we're going to see that local buckling tends to affect short columns more than any other kind of column. Did anyone who picked short columns feel comfortable sharing why short columns came to mind instead of long or intermediate columns? Anybody? Okay, I didn't make this a scary question just because it's Halloween. We'll talk about why these are more likely to affect short columns. The answer I usually get is because I show you pictures of short columns. So that's one reason. But what we're going to see basically is the longer the column, the more likely it is that we'll get global buckling at lower stresses. This local buckling tends to reduce the total cross-sectional stress we can apply to the section before we get local buckling. And basically what we're going to see is that for short columns that want to get to the full AFY load, they're not going to be able to get to the full AFY load because they're going to have local buckling first. And that's going to basically reduce the overall stress that we can achieve on the cross-section, and that's going to reduce basically that flat line that we talked about the other day. All right, the flat line there is plastic cross-section. That's basically the AFY load. And we're going to see that because local buckling can happen before we reach the yield strength, that line is basically going to shift. But the closer we get to the oil elastic buckling load, the more likely that column is going to buckle under a smaller cross-sectional stress than the stress that would cause local buckling. And basically what we're going to see is we're going to get something that looks basically like this, depending on the curve that we're working with. We're basically just shortening this curve so that we reach the AFY term at a slightly lower load. We're going to get that flat line with an effective area. And then we use the same equation to approach that Euler elastic buckling load. And we'll talk a little bit about why that might be. So the first thing we need to do is actually evaluate what local buckling is, because it's perhaps simpler to think about what it looks like in terms of the pictures and videos that I've showed you before. But we need to be able to quantify these things. It's not just important that we can describe them, but we have to quantify them too. Basically what we've got is if we have a relatively short column and it's under relatively uniform stress from the compressive, so we've got an axial force acting on this column, what we're going to do is we're going to divide up this cross-section into the equivalent plates. Okay, so we might be able to conceptualize that on the right-hand side here as 2 little plates here for the flange, a plate in the middle for the web, and 2 plates over here for the other flange. And what we're going to do is we're going to separate out all of those plates, and we're going to look at the stress that's on them, And we're also going to look at the support or the boundary conditions. Okay? This is a little bit strange because you've never evaluated a plate buckling problem before. It's more of a graduate school level topic. But what we're going to do is pull out one of the flanges. So we'll pull out one plate of this flange here. We're going to pull out the web. And what that's going to look like is something like this. We're going to treat the flange as if it's essentially restrained along just one edge here. It's restrained because it's connected to the web and the flange at the other location. And so we're going to assume that this can't translate in or out of the page or this way. It's fixed for moving along the one edge only, and it's also sort of fixed for moving longitudinally at the top and bottom. But this edge is free to buckle. On the web here, we're going to do more or less the same thing. So the left edge here is prevented from restrained from moving in translation. So is the right-hand side because both edges of the web are connected to the flanges. We're going to assume that the flanges prevent them from translating at those edges. And all of these plates are carrying essentially the same stress. Okay, so they're carrying the same stress, which is P over A for the full cross-section. And what we want to do is we want to see at what stress this plate is going to buckle in a similar way that a column would buckle globally under axial compression. I don't want to get too theoretical here because it's not useful, but I do want to show you what the buckling shapes look like so you can conceptualize a little bit more what local buckling looks like for the flange or for the web, and then I'll show you an equation that we use to calculate what that stress might be. Okay, so basically once the web or flange reach the stress that will cause critical elastic buckling, because the flange is restrained on the right edge and the left edge is not, the left edge is essentially going to buckle in a waveform something like this, which is interesting, and then the web, because it's restrained on all edges, it's going to buckle basically between all of the edges of that plate. So it's basically going to cup in and out. We have this sort of waveform for the web that I guess looks something like this. If we were to look at it through the middle of the plate, buckling something like that. And the flange is doing something similar, buckling something like this. And if we were to look at it, it's kind of buckling in a bunch of different waveforms. What we're not seeing here is a flange just buckling straight outwards, and we're not seeing the web buckle straight outwards, right? We're not observing that kind of behavior. We're observing essentially the formation of several waveforms along the length of this flange, and basically the stress that causes this buckling doesn't change with how long this plate is. It might change a little bit for really, really short columns, but we don't often have really, really short columns in our structures. They tend to be of intermediate length. And so what we're going to see is that the stress that causes this buckling to happen does not depend on this length, right? So it does not depend on that. It's actually going to depend on the width of the plate, in our case D for the web, and the thickness of the plate. And specifically it depends on the D over W ratio for the web and the B over T ratio for the plate steel, for the flange. Okay. Does anyone have any questions about what's going on here and what it is that we're trying to quantify before we continue on to the equation that represents this problem? Okay. Ultimately, if the plates are really thin, they're going to buckle before we reach the yield stress in those elements, and when they buckle something like this. The stress that causes that kind of buckling to happen is different for the web and for the flange. They're not going to buckle at the same time. Normally, one or the two will buckle first. And the equation that we can use to quantify the elastic stress that would cause buckling looks a little bit scary because we see some K and we see nu, which we haven't seen for a while perhaps. I think you talked briefly about nu mechanics of materials and not very much after that. You don't really need to know much about nu other than the fact that nu is usually 0.3 for structural steel. And in fact, we're going to see we don't really use this equation at all in steel design, but the stuff that we do use is based on this equation. It doesn't look too different from Euler elastic buckling load for columns. We still have a pi squared and an E in there, except now instead of the KL over R ratio, we have the plate width to thickness ratio. Okay? This K value basically just depends on what the boundary conditions are. If it's more restrained from moving, K is going to be higher. If it's less restrained from moving, K is going to be smaller. So for the one edge pinned case, which might represent half of the flange of a wide flange section, before what I showed you is what it looked like if the edge was just restrained from translation, but if we actually also clamped the edge and prevented it from rotating, that's going to increase K a little bit, and the same thing for the web. If we prevent those edges from rotating in and out, then that's going to increase the stress as well. Generally speaking, we tend to err towards the sides of being slightly conservative, so we generally look at the lower case of having the one edge or two edges pinned against translation and not against rotation. Now, you don't really need to know much more about this equation other than this is the effective length, BEL. It's the elastic buckling width of the plate. This is BEL for the web. Normally, we quantify that as H, which is equal to D minus 2T, and I'll show you that later on. And when we talk about the width of the flange, we talk about this as being B over 2. Okay, this BEL is going to be confusing because we're going to see oftentimes we just think about B. B is the width of the plate we're looking at, but B might be B over 2 because we also use B to quantify flange width. Okay, so you just have to be careful with what B means here in the different contexts. If we wanted to force these plates to yield before they buckled like this, how could we arrange this equation to figure out perhaps what BEL over T ratio would allow us to force these plates to yield before reaching this critical elastic buckling strength? How could we approach the problem of figuring out what B over T ratio we need to make sure the plate yields before it buckles? Any ideas? So FCR here it's a compressive stress. That's the compressive stress on the flange or the web. And perhaps we could say, maybe that should be greater than Fy, right? If it's bigger than Fy, we're more likely to get yielding of the cross-section. That's similar to that Euler elastic buckling load versus yield load curve that we looked at previously. All right, so we might say, okay, let's make FCR greater than Fy. And if we do that, we can rearrange all of the stuff in this equation and figure out what BEL over T has to be equal to or less than so that we get FCR exceeding Fy. So if we want to stop local buckling from happening, we can calculate this BEL over T ratio and make sure it's less than all this stuff in the square root divided by square root of Fy, right? This is rearranged, this equation. That process is not super important for us. What is important is that this is a constant depending on boundary conditions. E is a constant, pi is a constant, nu is a constant. And so these properties do not change with structural steel strength or grades. The only thing that really changes is Fy. And so what we end up with here is basically just a number. Okay? That number is a constant that depends on K, and K can be different depending on the different situation. So basically what that means is that BEL over T has to be less than or equal to some number divided by the square root of Fy. And so what we're going to do is for the flange and for the web, we're going to calculate the width to thickness ratio of the plate. And as long as that width to thickness ratio is less than this upper limit, we're going to say, okay, we're not going to get local buckling before we get cross-sectional yielding. And then we can use the equation we talked about on Monday and not worry about local buckling. If we do that just based on elastic theory, we have for one edge fixed cases, which represent the flanges of W's or WT's or C's, and for the two edges fixed case, which might be webs of W shapes or walls of HSS, numbers that look something like this. Okay, so BEL over T for flanges, if we want to prevent local buckling from happening, has to be less than or equal to 467 over square root of Fy. Similarly down here, a slightly larger number. And the numbers are larger for two edges fixed, simply because if we come back to this slide here, K is bigger for the two edge fixed case because there's more restraint against buckling in that case. And so we can get away with slightly thinner or higher width to thickness ratios when calculating that ratio and preventing local buckling for these situations. Does anyone have any questions about that? Let me just summarize briefly. We had an equation to calculate the critical stress that would cause local buckling. We rearranged it to exceed Fy. And when we do that for different constants K, we can simply rearrange this to get BEL over T for the different types of plates in our cross-section. As long as that ratio is less than a number, we can calculate quickly. We're preventing local buckling. Are there any questions about that before we continue on? Okay. So, problem is we can't use these numbers. And the reason we can't use these numbers is because just like for the Euler elastic buckling equation, we're assuming small deflections, which is fine, uniform cross-section, which is fine, loads applied at the centroid, which is fine. But we're also assuming the member always behaves elastically, which on Monday we said was not fine. We assume that the member is perfectly straight until it buckles, which again on Monday we said is not fine. Nothing can be perfectly straight, right? We cannot make it perfect. And that the member is free from initial stress before the load is applied, which again, for cross-sections that are hot rolled, that have significant residual stresses, is also an assumption that is not okay. So I'm going to wave my hands a bit and show you, once we consider all those bad assumptions and use better equations based on tests and analysis, the new values become, for flanges, BEL over T has to be less than or equal to 200 over the square root of Fy. For two edges fixed, BEL over T has to be less than or equal to 670 over the square root of Fy. And these have been more or less validated by tests, which is always something we want to have done when we're doing structural engineering. We can't just rely on elastic theory for all of the reasons that we had described previously. Okay. So these are the ratios that we're actually going to be using for design. These are just for a couple situations for single edge fixed for a wide flange section, or two edges fixed for webs or wall thicknesses of HSS. There are other situations like angles. They have a slightly different ratio, and I'll show you what that looks like here in a second. How does all this stuff come into play for us in terms of the S16 standard for design and construction of steel structures? Chapter or section 11.2 is called maximum width to thickness ratios for members in compression. And this is the section of the standard that tells us what ratios we have to stay within in terms of the upper limits on B over T to prevent local buckling from happening. So here it says the maximum width or sometimes diameter for pipe sections to thickness ratios for compression elements subject to axial compression are going to be in table 1. And so in table 1 of the standard, I'll show you that in a minute. This is the table that has the number divided by square root of Fy requirements as the upper limit for the width to thickness ratios for different situations. And those of elements subject to compression in members in flexure or combined flexure and compression come from table 2. We're going to start talking about that in lecture 26, and we'll also talk about it in lecture 34 or 5. Later on, we're going to see this. Sections that exceed limits presented in table 1 or table 2 are going to be classified as something called class 4 sections. We'll talk more about what class 1, 2, 3, and 4 means for flexural compression. We tend to classify sections, and it's more important for strength for beams, not as important for columns. As long as we don't have a class 4 section, everything is, for the most part, okay, and we can continue to use the expression that we talked about on Monday. Table 1 is, I believe, spread out more than just this. I think this is just an excerpt of table 1. But here's that 200 over the square root of Fy that we saw for flanges of I sections or T's or channels. Not important for us in this class. Stiffeners of plate girders, we'll talk about that in 5063. Legs of angles is a little bit different. It's restrained along one edge, but because we just have the two plates, it's a little bit more of a strict requirement. So for legs of angles, we have 250 over Fy, square root of Fy, and for stems of T's, 350 over the square root of Fy. For sidewalls of rectangular hollow sections or webs of different kinds of sections, there's that 670 divided by the square root of Fy that I had shown previously. Okay, so this table basically says, based on tests and data, informed a little bit by the elastic plate buckling theory. These are ratios, which are numbers that our B over T has to be smaller than in order to prevent local buckling so that we can use the same equation that we talked about Monday. Does anyone have any questions about what's presented here in this table and what that means for us before we continue on? So what does that mean for us in terms of calculating B to T? We've got limits. I talked a little bit about what B over T might be for different situations. S16 has some prescriptive guidance for what we need to do to calculate BEL and calculate the B to T ratio. So it has a bunch of stuff, some of which I'm not going to cover in CE 3063. Basically in this course we're going to focus on legs of angles, flanges of channels perhaps, or stems of T sections. And in that case we take the full nominal dimension, which means when you go to the handbook and you get B and D for an angle, you take B or D when calculating the width to thickness ratio. For flanges of beams and T sections, we take 1/2 of the full nominal dimension, and I'll show you what that looks like in a picture on the next slide. For elements supported along 2 parallel dimensions, this is important primarily for rectangular hollow sections, or HSS. Basically, we take the nominal outside dimension minus 4 times the wall thickness, and I'll show you why. And then for webs of hot rolled sections, we take H, which is clear distance between flanges. So that's great. Words are helpful, but pictures are worth 1,000 words. What does this mean for flanges of wide flange sections? Well, basically, B, that's the full nominal dimension. And so when we do local buckling calculations for the flange, we use 1/2 of the flange width, and so BEL is B over 2. When we do local buckling calculations for webs of the flange, or webs of the W wide flange section, we take the clear distance between flanges, which is underside of flange to top side of flange, and that's D minus 2T. For HSS, it's a little bit different. Basically, we're just taking the dimension of the flat part of the wall. The radius of curvature of the corners is going to be equal to the wall thickness. If they make it smaller than the wall thickness, they're going to start tearing the steel when they fold the plate around to make this square shape. And so we have the wall thickness, T, we have the radius of the corner, T, and we have that on both sides. And so when we subtract the radius and the wall thickness, we're subtracting a total of 4T. The last part there, the legs of angles or stems of WT sections, even though the stem, right, is only protruding out from the bottom of the flange, we still take the full nominal dimension D, in this case for stems of WT sections, or the leg lengths for angles, equal leg angles or unequal leg angles. Okay, so just to summarize here briefly, from this equation here, we figured out that our width to thickness ratio needs to be less than or equal to some number over Fy. S16 tells us what that number should be in table 1 for different situations. And then the BEL over T ratio is calculated in this way, depending on the part of the section that you're going to be looking at. Okay, and as long as BEL over T is less than the number from table 1, we don't get local buckling, and we can use the equation we talked about before. Questions? Okay, so let's come back here. This is the part that I did not talk about on Monday. We calculate the factored compressive resistance of compression members using this equation when the shape meets table 1 requirements. Okay, so when you check BEL over T or H over W, whatever the ratio is, and that ratio is less than what's in table 1, we can use this equation. When we don't have a section that meets the table 1 requirements, 95% of the time what that means we're going to be doing is we're going to be calculating an effective area of that cross-section that can meet table 1 requirements. So basically we're going to be getting rid of the section that extends outside of what meets table 1 requirements. I'm going to show you what that looks like, but basically we're going to just be reducing the elements that don't meet table 1 requirements so that when we calculate the compressive resistance, and we come perhaps way back here, that's the part that's going to account for the fact that for shorter sections of that column, we're going to get local buckling occurring at stresses below the yield strength. And so instead of reducing the stress, we're reducing the cross-sectional area to move that AFY line down to basically phi AE FY. Okay? So that's basically the form of the equation we're going to be using for sections that don't meet Table 1 requirements. And so it's no different. The only problem here, lambda is calculated the same way. You don't reduce the section for lambda. Fy is the same, n is the same. The only problem is if we have a section where we have the flange or the web not meeting Table 1 requirements, we have to reduce the area effective in compression. So what does that mean for us? Well, it says here we reduce the area using, or we calculate the effective area using reduced element widths that meet Table 1 requirements. And so if I was to quantify this in terms of a wide flange section, if we have B, which is down here, B, and we have BEL, which is B over 2, if that exceeds the 200 over the square root of Fy limit, I'm going to calculate an effective B value, right? And so the effective B value that I'm going to use, I'm just going to basically rearrange here. So if I had BEL over T, that had to be less than or equal to 200 over the square root of Fy. And BEL is B over 2T, because we're using B over 2. Then we basically say, okay, if B over 2T exceeds 200 over the square root of Fy, we're going to calculate a BE value that's shown up here, which is 2 times 200 over the square root of Fy times T. Or you could just say 400 over the square root of Fy times T. And that's going to be less than or equal to the B value that didn't meet Table 1 requirements. Similarly, for the effective height, this one's a little bit weird because we're not taking it away from the edges. We're taking some area away from the middle of the web. And similarly, if we have an H value that makes H over W greater than 670 over the square root of Fy, we'll rearrange that to get an effective H value. HE is 670 over the square root of Fy times W. And we use those new cross-sectional properties to calculate the effective area. Basically what we're saying is that because these elements are basically going to cause us some local buckling issues, we're going to ignore those parts of the cross-section and continue to use the AFY expression, but with this reduced area AE. Does anyone have any questions about that concept before I show you one other example? So this is wide flange sections. Okay, we get rid of the tips of the flange and the middle part of the web, and then we add the blue rectangles together with the red rectangles and get our effective area. It's less common. I would say it's uncommon. Okay, so this is uncommon to have wide flange sections that don't meet Table 1 requirements. There are a couple wide flange sections that are class 4, which means they don't meet Table 1 requirements. It is more common to have angles that don't meet Table 1 requirements. And the reason I'm showing you this one is because it's more common. And we also use back-to-back angles quite often as braces that might carry compression and tension together, or sometimes it's tension only, depending on how you're designing the system. In a similar manner, we have the total width B, which might be this width. Right, so that's B. The height of this leg here is D. We base the local buckling checks. So one is D over T, the other is B over T. Both of those have to be less than or equal to 250 over the square root of Fy. And if either one is greater than 250 over square root of Fy, we're going to get rid of the parts that cause us issues. We're going to calculate an effective D value and an effective B value that meet Table 1 requirements. It doesn't always mean that both legs will exceed Table 1 limits, but for these types of situations, it's quite common for the long legs, right? So long leg It's more common for the long legs because, well, the D value is bigger, but the thickness is the same always for the angles. It's common for the long legs to exceed typical 1 limits. And so it's not uncommon for us to have to calculate an AE value, which comes from adding up the rectangles. The one thing here you might see is this minus t squared part. The reason I have that in here is because when we're adding up these two rectangles, we have this area of overlap, right? And so we need to take that out. And I suppose I don't have that inside the brackets for some reason, so that should be minus 2 times t squared. So, or we could rewrite this as 2 times, well, no, I'll just leave it like that. 2 times BE plus DE times T minus T squared, because we're overlapping those rectangles in 2 spots, and T squared is multiplied here by 2. Okay. We're going to do an example using long leg angles or unequal leg angles to calculate AE. But before we do that, does anyone have any questions about anything we've talked about so far this morning?
Did you say
Minus 2t squared. Because there's 2 overlap areas, right, of that angle. So the left-hand side, the blue rectangles overlap. The right-hand side, the blue rectangles overlap. So we need to get rid of that by subtracting 2t squared. All right, so local buckling can happen if the B over T ratio is less than a certain number over square root of Fy. When we have that case, if we do have the local buckling occurring, we recalculate effective properties for the section and use that to calculate an effective area. And then we can plug that into the expression that we've used, but now with a different area that's reduced to account for the local buckling effects. If I was to put that in a little point-by-point procedure, basically we're going to start by getting cross-sectional properties from the handbook. We're going to calculate Fe and lambda. We don't really care about local buckling for those 2 properties. We just calculate Fe and lambda. Then we're going to check whether the width to thickness ratios meet the Table 1 requirements. If either of one of them don't, then we have to calculate the effective area, where the effective widths of the plates meet Table 1 requirements, and then use the AE term to calculate the compressive resistance. Otherwise, it's business as usual, and we already looked at that example on Monday. Okay, so what we're going to do here is we're going to look at a set of back-to-back L152 by 102 by 7.9 angles. We're going to assume they're being used for tension and compression loads. If they were tension-only bracing, don't care about local buckling because we're not dealing with compression anyway. But if we're expecting to get some compressive resistance out of the brace as well, when we calculate that compressive resistance, we have to account for the potential for local buckling to happen. So what we're going to do today is we're just going to determine if the section is susceptible or not susceptible to local buckling. And if it is susceptible to local buckling, we will calculate the effective area. Okay, we're not going to get to the compressive resistance calculation, but we will calculate the effective area for this cross-section based on the potential for local buckling. Does anyone have any questions about what the example is asking us to do before we get into the calculations? Okay. So how do we start this problem? What's the first thing we need to do? We're not going through this entire procedure, but we do need to get some cross-sectional properties, right? Because basically what we need to do is check B over T for the short legs and D over T for the long legs, and we need to compare those to the Table 1 limit for local buckling. Okay, so from the handbook, and actually from the cross-sectional designation here, we can get B is 102. Okay, so B is 102 millimeters. D is 152 millimeters. Those come from the nominal dimensions. And the last one, right, is the leg thickness, but remember 7.9 is not the actual thickness. It's close to the actual thickness. And technically, we're allowed to use this number for local buckling calculations just to make things simpler. But if you go in the handbook, you will see that the T value given there is 7.94 millimeters. Okay, so there's that extra small little bit of thickness that we might want to consider when we're doing our width to thickness calculations. Okay, so for the short legs, we have B over T, and that's going to be equal to 102 millimeters divided by 7.94 millimeters, and that's going to give us a ratio of 12.8. Okay, so why are we using B here instead of B minus T? Well, that comes back to 11.3 that says for legs of angles, we use the full nominal dimension. Okay, so when we're doing legs of angles, we're using this full width B, which is 102, and the B to T ratio is 12.8. Any questions about that before we do the long legs? Okay. So next we're just going to do the long legs, get the B over T ratio. And for the long legs, again, when I do B over T, that's a common just width to thickness calculation for plates. B in this case happens to be B for the short leg. When we're doing that calculation, we use the D value for the long leg. Okay, so the width to thickness ratio for the long legs is D over T. That's 152 millimeters divided by 7.94 millimeters. And when we do that calculation, we get 19.1. Okay, so as expected, longer legs, width to thickness ratio is higher than the shorter legs because the nominal dimension is bigger. So we've got two width to thickness ratios. Do we have enough information yet to determine whether or not we will get local buckling or not? What do we have to compare this to? Yeah, we need to compare this to the upper limit given in Table 1. So if you go to Table 1, which I have here in the slides, it's also on page 1-185 of the handbook. Legs of angles is number 2 here on the slides, and BEL over T has to be less than or equal to 250 over the square root of FY in order for us to not get local buckling. Okay, so I'll just do that calculation up here. 250 over the square root of Fy. Fy is 350 because we're using 350W steel. 95% of the time, angles are going to have 350W steel. So we divide by the square root of 350. And when we do that calculation, we end up with a ratio, or upper limit, of 13.4. So what does that ratio tell us about the short legs and the long legs? Are we going to have local buckling in the short legs? Yes. No. No, we're not going to have local buckling in the short legs. The width to thickness ratio is less than 250 over square root of Fy. For the long legs, though, right, that's quite a bit higher. I mean, relatively speaking, this is just meeting the limit, right? This is exceeding it by a reasonable amount. And so what that tells us is, this exceeds 13.4, and so we're going to get local buckling before yielding. And that means we need to calculate an effective area using effective leg lengths for the long legs. Okay, we can get the full 102 millimeter width of the short legs active. We're going to recalculate an effective D to calculate an effective area that we could plug into the expression for CR. Are there any questions about why we've made that conclusion before we go ahead and calculate AE? All right. So we already have a nice example here for double angles, how to calculate AE. We don't need to do anything with B here, because if we did this calculation, we already know that B over T is less than 250 over square root of Fy, so if we calculated BE, we get something bigger than B. We cannot add steel to our section because the width to thickness ratio meets the requirements. But for the long legs, DE is going to be something that we need to calculate, and that's going to be less than D, right? So we're basically calculating the length of this smaller rectangle here, and then we can calculate the effective area, in our case using BE is equal to B, and a value of DE that we calculate. Okay, so we need to calculate the effective leg length DE. That is going to be equal to 250 over the square root of Fy times T. We've already calculated 250 over the square root of Fy for us, right? That means we're going to have 13.4, right? That's the width to thickness ratio up here, 13.4, multiplied by T, which is 7.94. The effective length for the long legs is going to be 106 millimeters. That's not that different from B, right, the short leg. And one of the things that might tell you is that for compression calculations, maybe you don't want to do a 102 by 152. Maybe you would just do a 102 by 102, right? In that case, both legs would meet the Table 1 requirements and you wouldn't have local buckling. But it is common to have a slightly longer leg to fit some bolts in and stuff. So it's not always, just because you do this calculation and see, okay, well, I'm really only going to get 102 or so, 106 in this case, millimeters effective. It may be just a practical consideration in this case that I picked slightly longer legs so I can fit some bigger bolts or something like that. But that tells us that we're basically not getting a whole lot more effective area than we have available in the short legs for these angles. Okay, so if we come back and look at the equation here, I'll get rid of some of this other stuff that's in the way. Basically, when we're calculating AE, we get 2 times BE plus DE times T. Here, because BE is less than or equal to B, we're just going to use the B value here. And so when we calculate this effective area, we're going to have AE is going to be equal to 2. For us, BE is equal to B, so we'll just use B plus DE minus 2t squared, and I'm missing it multiplied by t there. So 2 times b plus d multiplied by t minus 2t squared. We get 2 times 102 millimeters. Oops, don't want a bracket there. Plus dE, which is 106 millimeters, times t, which is 7.94 millimeters. And then because we're overlapping those two rectangles, we have to take away the 2t squared part, minus 2 times 7.94 millimeters squared. When we do that, we end up with an effective area of 3,179 millimeters squared. Now, it might be useful, like we'll just quickly, I'll tell you, I guess, for a single angle over here in our example, I'll get rid of some of this stuff in the way. One angle on its own has an area of 1,950 millimeters squared. That means the total area for the cross-section is 2 times 1,950, which is going to be 3,900 millimeters squared. When you do an AE calculation, you want to make sure that AE is less than A. You cannot get more steel magically by doing this calculation. And if you're doing a spreadsheet calculation or something and you're not doing this quite right, you could accidentally add up with more area than you have available in the cross-section. We've got 3,900 total. We've got 3,179 effective. That's less than the 3,900, but not too much less. It's less than the full area by 25% or so. Okay? So not a significant reduction, but it's going to reduce the strength certainly a little bit, but it's going to affect the strength more, basically. Well, actually, that's a pretty good example because we're basically something like here. So if our double angles were really short, we're getting something like a 25% reduction. But the longer our angles get, we get closer to the Euler elastic buckling load, which is not affected by local buckling. And so if our angles are out here, it doesn't mean we're getting a similar 25% reduction in strength, but we will get a slight reduction in strength compared to if the section did not have local buckling. Okay, so just quickly here, we've got a double angle which had a total area of 3,900. We calculated the width to thickness ratios for the short and long legs. Short legs were fine, long legs were not fine. They didn't meet the 13.4 limit from table 1. So we calculated the effective D value, used that to calculate the effective area that would be able to reach the yield strength and compression. And when we calculate that effective area, indeed it's less than the total area, which is a good double check to make when you're doing these calculations. Does anyone have any questions about the example before we move to summarize what we talked about today? Okay, so now you should be able to describe local buckling in members under axial compression, check whether a section is likely to experience local buckling prior to cross-sectional yielding. We do that by calculating B over T, making sure it's less than the table 1 limit. And then if it's not less than the table 1 limit for all of the elements in the cross-section, we calculate effective widths and use those effective widths to calculate effective areas of the section when they're susceptible to local buckling. Does anyone have any questions about anything we talked about in lecture this morning before wrapping things up for the weekend? All right. Enjoy your Halloween evening, everybody. We'll see you on Monday morning.